Today, we're going to use these slides to break down a huge paradox that's sitting right at the heart of modern computing. You've seen it, right? The spec sheets for new processors keep getting more and more insane. More cores, more threads, just more raw power. And yet, for the really demanding stuff, our operating systems just seem to be hitting a wall. It's like we've built this incredible 64-lane superhighway, but we're all still just sitting in traffic. So what on earth is causing this jam?
Well, at the heart of this whole thing is something called the many-core processor problem. And get this, it's not just a case of diminishing returns, it's a situation where adding more horsepower can actually make things slower.
I mean, just to get a real sense of the scale we're talking about, look at this. Not too long ago, we were all excited about having 2 or 4 CPU cores. Now, we've got specialized chips like the Xeon Phi that are packing, over 64 cores and more than 300 hardware threads. The operating systems we use every day, they were born in that older, simpler era. They just weren't built for this kind of parallel power. Okay, so let's drill down and get specific. Where's the breakdown happening? Well, a huge part of the problem is this invisible component called the OS scheduler. Think of it as the air traffic controller for your CPU. It's deciding what goes where and when. And as some really fascinating research shows, that controller is getting seriously overwhelmed. And this quote, this is from the research paper I'm talking about, one that introduces a new scheduler they call FLSCH, and they are not pulling any punches. They're basically saying that the default scheduler in Linux, one of the most important kernels on the planet, can actually sabotage the performance of the exact kinds of programs these fancy new chips are supposed to be amazing at. And this chart, it shows you everything you need to know. It's pitting their new scheduler, FLSCHED, that's the FL in those tall blue bars, against the standard ones in Linux. I mean, just look at that difference. FLSCHED is just blowing the others out of the water. We're talking up to 1.73 times faster. That is a huge deal. So how'd they do it? What's the secret sauce? Okay, so culprit number 1 is something called lock contention. And this analogy nails it. Picture a giant 64-lane superhighway. Total freedom, right? But now imagine that to get anything done, every single one of those 64 lanes has to merge down to pass through a single toll booth. That's a lock. It's a resource that only one core can use at a time, which means all the other cores just have to line up and wait. And here are the numbers to prove it. The default Linux scheduler, it uses 11 of these little traffic jams. Other schedulers, 15. And FLSCHED, the new one, a big, fat 0. By building what they call a lockless system, they just got rid of the traffic jam entirely. It's a whole new way of thinking. But that's not the whole story. There's another huge problem. See, traditional schedulers try really hard to be fair to every program that's running. But this creates a ton of overhead from something called context switching. It's like a chef trying to make 100 different meals at once. They're spending all their time just frantically switching between recipe books instead of actually, cooking. That's our OS, wasting time managing the work instead of doing the work. And this graph, wow. This graph is just wild. That red line climbing to the sky, that's the default Linux scheduler. You see it? As the work piles on, the wasted effort from context switching just explodes. It goes through the roof. Now, look down at that flat blue line at the bottom. That's FLSCHED. It's barely even moving. This is so important. It shows FLSCHED isn't just faster, it's smarter. It's achieving way more by doing way less. Okay, so we've seen how a clever scheduler can totally change the game. But what if that's just putting a fancy bandage on a much deeper wound? What if the real problem is the entire philosophy behind our modern operating systems? Which brings us to a pretty radical thought. What if the key to ultimate speed is to just say no to all of it? And that brings us to this, bare metal OS. Now, this is not your everyday operating system. It's something called an exokernel, which is just a fancy way of saying it is stripped down to the absolute essentials. I mean, it's written entirely in assembly. That's as close to the bare hardware as you can possibly get. It's all about ripping out every single layer of abstraction to chase one thing and one thing only: raw, blistering speed. And the way it handles multitasking, it just completely sidesteps all those problems we were just talking about. There's no complex scheduler trying to juggle a million things. Nope. Bare metal just gives one task to each core, and that core works on that one thing until it's done. Period. The result? Absolutely zero context switching. It's just a totally different way to look at the whole problem. And being this minimal has some pretty mind-blowing side effects. The whole operating system, the entire thing, needs just 4 megabytes of RAM. 4. That is less space than a single photo from your phone. It's just a crazy reminder of how much bloat we've all just kind of accepted as normal, right? So, okay, we've looked at a really smart fix for the current system and then this super radical alternative. But what's next? Is there a middle ground? What if you could get the raw speed of something like bare metal, but with the safety and features of a modern OS? Well, let's sketch out a blueprint for what that might actually look like. So this theoretical OS of the future would be built on 5 key principles. First, a single address space. Put the kernel, drivers, apps, everything in one big shared memory space. Second, something called domain fusion, which basically lets you merge software components on the fly for a speed boost. Third, a distributed multikernel. You start treating each core like a tiny node in a network. Fourth, zero-copy I/O, which is a clever way to pass around data without actually moving it. And last, direct interrupts, which lets your hardware talk straight to the drivers, skipping the kernel middleman.
Now that first one, the Single Address Space OS, or SASOS, is probably the biggest deal. The best way to think about it is like a house with no internal walls. It's just one big open floor plan. Moving from the kitchen to the living room is instant because there's nothing in the way. By putting everything into that one memory space and then using modern hardware to put up virtual walls when you need safety, you could get the best of both worlds, all the speed with all the protection. So, when you boil it all down, what we're really talking about here is a fundamental choice. We're at a crossroads, really, facing a major trade-off in how we design the very brains of our computers. On one side, you've got the old guard. These are the big monolithic kernels like Linux. Monolithic just means the whole OS is basically one giant piece of code. They're designed to be a jack of all trades, great for general use, packed with features, trying to be fair to everyone. And then on the other side, you've got this new wave. These are microkernels and exokernels, and they are specialists. They are built for one reason and one reason only, to squeeze every single ounce of performance out of the amazing hardware we have today.
And that leaves us with one last kind of provocative question to chew on. What if we've been pointing the finger at the OS for too long? Maybe the real bottleneck isn't the operating system at all, but the applications we build on top of it. The habits we formed, the code we reuse. To really tap into the insane power of these new machines, maybe rewriting the OS isn't enough. Maybe we have to be ready to rewrite all the rules.